My name's McGushion, and I started XL Orbital Systems when I was 24 as a robotics welding company. But here we go. Obviously, the work we're doing now is primarily on F-35, and we image what's called the inlet bump for bird strikes. The medical market, you probably already know this, but it's sort of the tee up. 17.9% of GDP spent on medical in the United States, which shocked me. We spend more on healthcare, and imaging increasingly is the leading reason why. Doctors, before they do a diagnostic, they want to do a picture, or before they do some recommendation, they want to see a picture. The global market is large, up to $45 billion projected by 2022. Aerospace, by the way, is $3 billion by 2022, which is the reason why Michael was so convincing. He goes, you really need to get over to medical as soon as possible. And when I saw those numbers, it made sense. So, 13.6 billion in North America. Here's the graph going to 2024 and the various segments of imaging. Which segments this may displace. It could be one, it could be all, it could be a combination of them depending on what you're imaging. And they're all increasing in size. I didn't know what a proximal interphalangeal was a month ago, and so last week I imaged it and
Googled it first.
That's an MRI image on the right side there, and you'll notice that as we went over the joint, that was the signature of the joint. And we'll fire this up in just a minute, and you guys can do that. So the question is, what are you seeing? Well, we're seeing differences in density, we're seeing differences in material, we're seeing differences in distance. And all of those things combined give you that signature. And much of what we do in M-Wave development is separating data out. And that's an incredibly difficult challenge, because, especially when you're looking at a strip chart like that, to control for one variable while looking at another, or controlling for a group of variables while looking at another. And we have developed a number of methods to do that, and you'll see some of those methods shortly. But we use basically a hybridized spectrum analyzer to look at some of that stuff. So this was the first impressive sort of look at the human body with this technology. And it's in what we call an A-scan. An A-scan is voltage out over time. Very, very simple display, strip chart recorder sort of data. But moving into 3D very shortly. This was fascinating because I had never done this before, but I put the sensor on my pulse, and we monitored on an oscilloscope, and I used an oscilloscope because it has much higher resolution. And I was able to get it with this system, and we can probably find it, but the signal was small. So with this, I suddenly became aware of this extreme detail in pulse. And so here I am monitoring my pulse. And this is monitoring blood flow through the vein, because blood is conductive, and we generally are visible to things that are conductive. In fact, that back up again. Where we see things that are conductive very well, but we also see things that are insulators, so we can measure capacitive effect, and that's why we can image things like plastic. This is the flow of the blood with the heart rate. And by the way, on an oscilloscope, if you take this sensor and you put it really anywhere on your body, you see this background pulse of the heart pumping. And it's a background signal that's in your body, obviously, all the time. But we're used to seeing it on a heart rate monitor or a pulse monitor, but not necessarily here. You can see it here or here. And which makes sense, because blood is pulsing through the body all the time. And that brought us to the realization that we already have 4D built into the system. And what I found in medical imaging, 4D means over time. So you're doing real-time imaging where X-ray might be a slice at this instant in time. You're not seeing motion. Even CT or MRI. Ultrasound probably comes closest to seeing 4D where you can see motion. And I don't know how much blood flow you can see in a UT image, but this brought us instantly, I felt, into this 4D arena, which I didn't really know that we could do. 4D, by the way, is wrongly used. Time is not the fourth dimension, so, but it's just used that way. It's completely new technology. People have not used, and it's specifically radio waves in the AM band, 600 to 800 kilohertz. Extremely low power, 500 millivolts peak to peak. It's basically 25 microtesla, as opposed to tens of thousands of Tesla in an MRI, which is hazardous, by the way. I mean, according to the FDA, it's hazardous. So we don't use ionizing radiation, which works well for hard tissue, bones, things like that. It doesn't work particularly well for soft tissue. Powerful magnetic fields, which work for soft tissue, not particularly well for hard tissue because of the presence of water, H2O. And it relies on the hydrogen atom specifically in MRI. And we don't use sound waves. And sound waves, UT, which is what we call it in aerospace, requires coupling, which if you've ever gone in for an MRI, they gel you up. And they even do that on aircraft, by the way. They gel it up, which seems ridiculous, but. And photosensors, the oxygen meter that you put on your finger, it's a photosensor. But limited in what it can see. It doesn't see even as much as I just showed you on the blood flow with M-Wave. I was looking online at a number of videos with light meter readouts, and our output is much more detailed. Last night we were asked, well, can it measure blood flow stoppage or blockage? And since it was so clear and precise in how much flow went through from an electrical point of view, I theorized that we should be able to determine whether or not you have adequate blood flow in different arteries or veins. And I'm speaking speculatively. I don't know. All I know is you put it on your body and you get these results. Why not investigate, build a prototype, and see just how much you can see? And my guess is you'll see a lot. So with M-Wave, from a material perspective, it appears to be sensitive to everything. Even glass. It can image glass, which from an electromagnetic perspective shouldn't be possible, but it is for a number of reasons. And so the challenge becomes separating data. And we'll get into that in just a second. MRI seems to be the big, imaging push in medicine. Everything's going to be MRI. But this is fundamentally different from that because MRI uses an extremely powerful magnetic field to impose alignment on the hydrogen atom of water. And water has to be present and is most present obviously in soft tissue. And then it does a flip on the magnetic field, which releases an electron in the radio wave frequency, but in the megahertz band. But only by way of imposing this very, very intense magnetic field. So there's a lot of equipment required. M-Wave allows the material to impose a resonant frequency on it. So it works in reverse, essentially. Instead of imposing a frequency on something, we allow that something to impose a frequency shift on M-Wave. I mentioned the A scan, which you looked at earlier, and it's basically a strip chart, something on an oscilloscope. B scan is a 2D image, top down, X and Y. And this is using M-Wave of that block of plastic with one of our XY scanners that we have. And then 3D, you begin 3D by basically creating a topographical map, which is where we're heading right now on our next generation sensor. where output it becomes the z-axis of the display. From there you go to 3D where you now begin to separate. You know, this layer is this thick, and so draw a line and put that object underneath that layer. So you begin to do solid modeling. And then from solid modeling you go to 4D, it's solid modeling over time. You watch the blood flow, the organs move, a baby move. So fundamentally, so I do all the electronic design, and so if I go too deep into it, just sort of ask a question. So you essentially have an LRC, inductor, resistor, and capacitor circuit, and the inductor is really the critical part of M-Wave, and there are two inductors. And we use one inductor to generate a transmit frequency. We use the second inductor to act as a receiver, a radio transmitter, a radio receiver. But we do it in such a way as to exploit a phenomenon, which I think is the next slide. And when we exploit that phenomenon, this method of measuring inductance, capacitance, reactance becomes uber sensitive. And where before, for instance in eddy current, you would only be able to measure things that were conductive in the inductive realm of things. But we're able to measure things that are in the insulator realm of things. A lot of different insulated parts. Plastic was one of the things that you saw with the 3D image that I just showed before. And so the reason is because we're sensitive to the reactance due to capacitance, and that's the X sub C that you see there. I won't go too deep into that, but if you want to later, you can certainly ask me questions. It's an animated GIF that I did of some testing that I did a while ago, and it demonstrates the phenomenon that I first saw years ago, and the reason I called it M-Wave. Here, we're moving along. Get my mouse working here. And as the transmit frequency increases, so does the receive frequency, until that flip occurs. You saw that flip happen? Mm-hmm. That flip is a very precise thing that happens in a very precise way, which, when it happens, suddenly becomes sensitive to a number of things that you previously couldn't see. It also allows you to isolate a number of variables. For instance, the effect of distance from an object. Because when you image, you obviously are changing distance quite a lot as you go through your hand or whatever. And it would be great if you could isolate that variable, or if you could isolate variables related to conductivity or capacitance at will. And so this allows us to do that. And it took me a very, very long time to figure that out. And apparently no one else ever has. Maybe some scientist in a lab somewhere has seen this before, but it's one thing to see it, it's another thing to then go exploit it. And that's what we do specifically in M-Wave. And this was basically the frequency response curve that I showed you. And you can see it begins to make this M shape as the two resonant frequencies approach each other. And that's why we call it M-Wave. Oddly, you would expect that as the transmit frequency matches the receive frequency, that would be the maximum output. That is not true. It happens adjacent to it. And even radio people, I tell them that. No, it would be at the matching frequency, because when you dial your radio station, you dial it to the frequency. That is not the optimum frequency when you have two inductors arranged like this.
Is that a superposition of like the natural frequency of the material you're going through?
It matters what you put in front of it. So everything that's in front of it affects these resonant frequencies, which is the good thing. The bad thing is everything you put in front of it affects these resonant frequencies. So that's why so much of the time is spent in signal processing and controlling of variables, because it's sensitive literally to everything. Here's the hybrid spectrum analyzers, and I won't go too much into this, but essentially a spectrum analyzer sweeps frequencies, finds out what frequencies you're broadcasting at, and how many dB of gain is at the various, how much gain you have at these various frequencies. What we've done is sort of a rotational spectrum analyzer, because what we'll do is we'll sweep through frequencies transmitting, and then we'll sweep through these same frequencies with a monitoring device, in this case an oscilloscope. In the case of the next generation one, there's a chip. It's called a miniature spectrum analyzer on a chip. And so this has what we call 9 different artifacts on it. And I won't go into all those artifacts, but each of those artifacts is a way to control a variable. So if you want to control for something, you select an artifact as you're sweeping through them. And it allows you now to start building a solid model of what it is you're imaging. So one of the things that I'm doing is building a periodic table with M-Wave, where we're creating the resonant frequencies for the various materials. And you can see very much in that graph is insulators. And they're in a tight little spot there, but we can apply an incredible amount of gain to zoom into that and see great detail. But, you know, obviously conductors, but conductors are over in a band, and very much like a periodic table of elements. You know, metals are in a band. So things get banded relative to their resonant frequency. And this is probably, I'm a little too interested in that stuff. I get excited when I see it, so I can see the excitement is just overwhelming. Number 2, it's a propagating electromagnetic field subject to the inverse square law. So as you go farther away, the signal diminishes exponentially with the square of the distance. And there's no way to overcome that. Light, it's the same thing, but there are ways of compensating for it with signal processing. We know that this signal has shifted, and we use a number of methods, but one is phase shift. So we can tell how far away something is and what it had to go through to get there. And so we can tell distance, density, things like that. And then again, build a model based on that information.
Okay, so that makes sense. That makes the organic problem more challenging. Because you're going to have shifts as you're going.
Right.
Yeah,
and, well, the beauty of the body is it's conductive. It's generally conductive, except for skin, bone, but we don't care about the non-conductive parts because we can see that, but we can see conductive things even better, which is why we had such high resolution on blood flow, which I didn't expect. This goes to one of your questions, and it's the hybridization of materials. So we look through a material behind another, we look through a material of one type into another material of another type. How do we know that it's that type behind it? And here's composite and copper, and this is copper behind composite. So with the human eye, you can look at that and say, oh, I can see how you would hybridize that image to make it a combination of those two things. But this is something that neural networks is especially good at. It can spot that instantly and say, oh, you have copper behind a wall of composite that is this thick. Or you have bone of certain density and thickness behind the blood vessel or whatever that's this thick. I'm not trivializing the complexity of the human body, and it's very complicated, but we at least have foundational information to work from, how we would approach it. Having said that, we may end up with something completely different during the course of a 12 to 18 month development period, where when we get into imaging the human body, something I hadn't seen before, it's like, oh, obviously you would do it this way instead of that way. So I leave open the possibility for flexibility during development.